Okay, so today we're gonna talk about electrochemistry. There's a few thermo questions. We're just gonna work 2 questions today. Please do. I encourage you. Matter of fact, if y'all are not here, I gave this out in 6th period. Will y'all come get one of these? Here. No, I made copies of this during 5th period. So if y'all come get this, I'll get this out tomorrow. Yeah, but go ahead and get it so you'll have it to look at. I only gave you 2, Connor.
I know I got 2.
What about Lane? Give one to Lane, please. That was really mean, Connor. All right, so if you'll open it up to the electro part, which is going to be all right, page 13, guys. It's the one that has the lion on it. Page 13 and 14, it has the lion. 13's on the front, 14's on the back. So again, this is a good way for you to remember and a good way for you to review of all of the points of topics that we've talked about thus far. So let's go through and let's look at questions. This is question number 3 in the 2007 exam. So this is potentially what you could see on question 3. So the first thing I want you to notice is the drawing. There's a very, very, very important thing that is told to you right here. Power supply. What is that? What is this thing? This is a battery. There's 2 types of electrochemical cells. The first type had 2 names. Galvanic, and what was the other one? Voltaic. Galvanic / voltaic. Now, it was spontaneous or non-spontaneous. This one was spontaneous. And what it means by spontaneous is, does it produce volts or create or need volts? This one produced. It produced. I don't know why it's so slow. Okay, so the second one, yeah, that's what it is. What was the other type? Electrolytic. Very good. Electro. Okay, electrolytic. Now, electrolytic cells are what? Non-spontaneous. So that means they have to be what? They have to be forced. They have to have a power supply. These are forced to occur. So this reaction that you're looking at is what? Not battery. This is being forced. We're talking about this right here. Now, there's one acronym, and it may be on there. It may not be on there. Let me look and see if it is. Very good. That was my next point. Electrolysis. I don't see this on here. And it's this acronym right here. EPA. Anybody remember that one? No, it was not the Environmental Protection Agency. Okay. This is the electrolytic positive anode. So what we're figuring out here is that the electrode is positive at the anode. Now, what makes it different? What makes that different from the other 2? Anodes are negative normally, but in this case, now we may not need anything to know about this, but it's just a good jumping off point of what we're seeing. Now, what are these things right here? Huh? Those are bubbles. Okay? So, since they are bubbles, that piece of metal must be something specific. It's not dissolving. It's a piece of metal. Metal's not into bubbles. Okay? It's an inert electrode. What were those 2 inerts? Platinum or graphite. Okay? So platinum or graphite. And the reason we know that is because a gas is being produced. So it must be an inert thing because it's not a metal. So now let's read the wording. So we've already kind of figured that out. So let's read what the words say. And I picked that up simply from the picture itself. I didn't read a word. Simply from the picture, I've already figured this out. Now, let's add one more thing. What is happening here? What is copper? What's happening to copper? It's gaining, no. How is it reducing? It's going from a 2 plus to a what? 0. So this is reduction. And we have the red. The charge is going down. Yeah, reduction, the charge is going down. So this is the red cat OA, right? So what have they just told us this right here is? This must be the what? The cathode. This must be the anode. We've already established We've already established this one point. This is negative, and this is what? Positive. Simply from a picture, we've picked this up. Simply from a picture, we've just determined this is electrolytic. We've determined what the cathode is, what the anode is, what the signs are. Now, here's another important part. How did electrons always flow in an electrolytic cell? Anode to cathode. What was an easy way to remember that? A to C, alphabetical. The electrons are going to be flowing that way. Now, one thing Lane mentioned a second ago, another way we can tell that this is an electrolytic cell and not galvanic, one, it's in one container. This is a way you can tell it's electrolytic. One container, and the most important thing, Lane, would you say? No salt bridge. So this is number 2. No salt bridge. What's the purpose of a salt bridge? Very good, to balance out the charge. So there's no salt bridge, so this must be electrolytic. So we've got every piece of information we could possibly need thus far. So let's go to the words. An external direct current power supply is connected. What have they just told you in these big, stupid, huge AP words right here? An external direct current power supply? That's a battery. That is their big way of trying to say we're smarter than you, and we're going to use big, huge words to try to outsmart you. A external direct current power supply. Why can't they just say battery? Why?
Why couldn't you just put battery up there for us?
Because it'd be entirely too easy, and they don't want to make it easy on you. That's exactly why. So they're seeing how intelligent is this person taking the test. Well, guess what? You guys are intelligent. You can figure this out. And as soon as you see battery in electrochemistry, if you have to use a battery, you're forcing it to happen, and so it's electrolytic. It's connected to, look, 2 platinum electrodes. We've already got that figured out. Immersed in a beaker containing 1 molar solution of this. What is that? What kind of copper? Copper 2. And they told you that right there. Copper 2 sulfate. As shown in the diagram above. As the cell operates, copper metal is deposited. Now, what does it mean by deposited? It's stuck on. It's stuck on. So what we're saying is that copper 2 ion is sticking to one of these plates. Now, I drew it on that one for a specific reason. It's the cathode. What was that acronym about the cathode? It's a fat cat. So if you stick something on it, what's going to happen to that mass? It's going to increase. So we have fat cat. Now hang on. Now, the platinum is inert. It's not going to react. So will this get any smaller? No. The anode's not going to get smaller because it's platinum. It doesn't react. It's just going to just stay there. So it's producing the bubbles. That's why it would be considering the anode. Okay, so simply by looking at some words, we've figured out exactly. So this is the process I need you to go through mentally of knowing exactly what they're telling you and not. I've stopped right here and look at all the information. I tell you what, no, I'm already right here, and I've already got that much information out of this. I've gotten a ton of information simply by a diagram and a few words. So Copper is deposited onto one of them. Well, we know that one of them is going to gain mass, and that's the cathode. And we already know this is reduction, and that's the cathode, and so it must be deposited on that one. And oxygen gas is produced at the other. The two reduction half reactions for the overall reaction that occur in the cell are shown below. You with me? Okay. So, in this case, let's look at the question. On the diagram, indicate the direction of the electron flow. Guess what? We've already done it. We've already done it. So, we know that it flows from anode to cathode. So, from an to cat. It always flows that way every single time. So if you can identify the anode, you can identify the cathode, and then you can identify the way the direction flows. So we okay with part number one? That's an easy one-pointer, right? You get 1 point for that, so you may want to write that down. 1 point for part A. Let's look at part B. Write the balanced net ionic equation for the electrolysis that has occurred. Electrolysis that has occurred. So, now, my question is, let's look at this real quick. Did we already agree that this is the reduction? Okay, and are we agreeing that this is the oxidation? Now, what happens in oxidation? What happens to those values? They get more. So, what is oxygen in this case right here? Hang on. That's where I'm going with this. That's where I'm going. I want you to hold that thought, okay? Now, Jenna, look. Oxygen in this state is what? Why is it neutral? It's a gas, it's diatomic. Over here, what is it? So what's happening right there? What is oxygen's oxidation number doing? It's reducing. What's wrong? We need it to oxidize. So what does that mean we need for this equation to do? Flip. So this equation needs to flip. Is reduces. In this case, it's electrolytic. So that's oh, no. Hang on. Let me think. The more positive is reduced, and there's something about this that there's a reason why. What is it? Since this is non-spontaneous, it goes backwards. So in electrolytic, the less positive is reduced. That may be something you want to write down. In electrolytic, the less positive is reduced because you're having to force it to happen, right? Normally, copper would not be reduced and turned into copper solid. Normally, that wouldn't happen. So let's write the balanced reaction for this particular case. So, yeah, flip docs. I'm gonna turn this. I'm gonna go to the regular page, and use this. So y'all use y'all's. Okay. All right. Oh my goodness. We've always set this up the exact same. Red, cat, OA, and what? Ox and Ra. All right, so now we know what the reduction one is. It's Cu 2 plus 2 electrons goes to Cu solid. Now, we got to flip the other one. So I'm just going to put the arrow in the center. Reduction. This is H2O plus, very good, 2 H2Os plus yields O2 plus 4 H pluses plus 4 electrons. Now, there's one way I want you to remember this. Reduction, the electrons are on the what side? Reactant side. R and R. Reduction reactants, electrons. So what about the product side? You with me? The electrons are on the product side when it's oxidation. Now, when we do electrochem, we must balance each half reaction, okay? And then balance what? So step 1, balance half reaction. And then step number 2 is important. Balance the what? Balance the electrons. Are our electrons balanced so far? No. How can we balance our electrons? Multiply what? The top by 2. So are our electrons now balanced? Right here. Get one of those and get each of one of those. So have we balanced each half reaction? Have we balanced the electrons? 3, add half reactions together. So let's add the half reactions together. So what are we going to have on the left-hand side? 2 Cu, 2 pluses. Do we bring electrons down? No. Leave the electrons out. Then what? Plus 2H2O goes to what? Cu. Oh, yeah, very good. 2 Cus plus O2 plus 4 H pluses. Guess what? Very good. Thank you. Put the 2 right there. Yeah, don't forget to distribute that 2. You've earned 2 points. The most things that people are going to miss is they're not going to flip this and they're not going to balance the electrons. That's the part where you're going to miss the most. And in electrolytic, you've got to figure out which one to flip. Okay? The oxidation is always flipped, but the hard part is the numbers. Is in a galvanic, the oxidation is normally flipped. Okay. Any questions on this? Any questions? Okay. Let's go back and look at question C. This is where you're like, what in the world and where did this come from? What have we been talking about the entire time thus far on this problem? What subject? Batteries and electro. Where in the world did delta G just come from? Why in the world are they talking about it? What'd you say? In Fe. Very good. Talked about this yesterday. There are 3 things that tell you true spontaneity. And it's what factor? The geek factor. Delta G, gangsters are bad. Do you want to produce voltage? Yes. And do you want to produce products? Yes. And so that is greater than 1. So all these things tell us if things are spontaneous. Now, guys, here's the easy part. We've already established what type of cell this is. Is it electrolytic or galvanic? Electrolytic. Is electrolytic spontaneous or non-spontaneous? Non-spontaneous. So, we know something. Predict the sign of delta G. So, if E is going to be, if that's spontaneous, then what is not? Here, let's do it this way. These are all spontaneous on top, okay? And on the bottom, let's just say these are non-spontaneous. Well, what is the opposite? Okay, delta G will be negative. What will E? Sorry, positive. Okay, what will E be? Negative, and K will be less than 1. Well, we already know that E is non-spontaneous. How did we determine that? It was electrolytic. Electrolytic is what? Non-spontaneous. So what does that make delta G? Makes it positive. So delta G must be positive because why? This is a non-spontaneous electrolytic cell. Because the reaction is non-spontaneous. Because E naught will be negative and the cell is electrolytic which is what? Spontaneous or non-spontaneous? Which is non-spontaneous? Which is non-spontaneous? Non-spontaneous. Okay. Now, let's look at letter E. And I think this is one where... Oh, okay. I missed D. I'm sorry. Let's look at D. Let's scroll up. It says then calculate the value of delta G. Well, there's only one way that delta G is related to E. In fact. Or Nephi, if you prefer. Now, we flip this equation, correct? So what do we do with the sign of this? So we make it negative 1.23 plus 0.34. Add those things together, and what do you come up with? Negative what? 0.89. Now, why did I just do that? Because I need E naught. What's F? What was F? Faraday. 96,500. F again is Faraday, which is 96,500. Is it coulombs per? Is it coulombs per mole? Look on that sheet. Is it joules per coulomb? Look on that sheet. It should be on there. I think it's joules per coulomb too. That's right. Volts is joules per coulomb. That's right. That's right. It's coulomb per mole of electron. What is N? Yeah, no, not moles. Balanced number of electrons. So it was that canceled number of electrons. So balanced number of electrons. Now, I want you to think for just a second. If I have a negative out here, and this is a positive, and this is a positive, and this is a what? What is E? A negative. What is a negative times a positive times a positive times a negative? So delta G must be positive. Haven't we already determined that? Yes, we have. What was that balanced number of electrons we canceled? 4. So it's negative 4 times 96,500. So times that and then times that. Now, what unit is this in? Electrochem is always in volts, which volts is joules per coulomb. So I want to set this up in an equation and show it to you because I want to show you how mathematically it works. All right. So clearing this. Maybe this will work a little bit faster. So delta G equals negative N Phi. All right. So delta G is going to equal negative 4 moles of electrons times 96,500 coulombs per mole of electrons. Okay. And then E naught was negative 0. What? 889. Now, we said a volt is what? A joule per coulomb. So we're going to plug in a joule per coulomb. And I'm showing you this for a particular reason. What's wrong? So we're going to see what happens. Moles of electrons cancel, coulombs cancel, and we're left with joules. Delta G, delta H, and delta S are thermo units. Those are all units of energy. What is your only energy unit we deal with? Joules. So delta G. Anybody do the math? Which I have it right here. positive 340,000 joules. Now, here's the big kicker. Per mole of reaction. They want to see that. Now, where the heck did that come from? That's AP being jerks. Okay? It came from the reaction. Now, that's joules. Is that the most appropriate way to write this? Kilojoules per mole of reaction. So I really don't want you to freak out when they talk about E and all of a sudden they throw a delta G at you. I really don't want you to freak out because it's this simple. What if they asked you, all right, we have, they've been asking you about K the entire time, and then all of a sudden they throw a delta G at you. What is that equation? Negative rat link. What if they're asking you about E and then they throw in K? This one should make a whole lot of sense. Come on. Right? Why is that true? Because both of them are equal to delta G. So you can set them equal to each other. Where do the negatives go? They cancel off. So if they're talking about E all of a sudden, so is that plausible? They'll give you the equation sheet. Yes, F is on the equation sheet. But I think they use a different value. It's like, it's the whole value. We've condensed it. F. No, it's 96.5. It's actually on here. And it says coulombs per mole of electrons. So it's actually on there for you. Guys, please use that equation sheet. Please, I'm begging you. If you pop up, if you see delta G or E or something, look for something and plug numbers in. Just plug them in. I don't care if you get it right or wrong. Figure out a formula to use and just plug it in. But use the right one, hopefully. Okay, that's the key to all this. All right. E. Let's see. This is one that, to be quite honest with you, I did not do a very good job teaching. And due to time, I don't even know if I want to try to teach it to you now. Because I think it would be more detrimental than it would be good, personally. If they throw this at you, applaud them, say job well done. I've earned my 2, 3, 4, 5. No, that's the wrong question. 1, 2, 3, 4, 5, 6 points out of 10. 6 out of 8's rocking it, guys. You'll beat the national average. Say that again. Yeah. Ampere is a coulomb per second. It's stoichiometry is what it is. It's rough. I think it would be more detrimental than to even try to work it out for you. If you want to see it, I'll be glad to give it to you. Yep, you got to use Faraday's constant, and it talks about moles of electrons, and it's rough. It's rough. All right, let me just point this out real quick. They ask for volume. They give you a temperature and a pressure, and you've already got moles and all that other stuff. What do you think you're going to use there? Pivnert. Yeah. If you somehow come up with E, then I'm just going to tell you this. This is going to be Pivnert. Sure. Figure it out. Yeah. Absolutely. Figure something out for that, plug something crazy in. Whatever you get for grams, convert it to moles, and plug it in and go. You with me? No, you got to show them where the mass came from. Yeah, that's the only thing is you've got to be genius enough and ingenuity enough to say, well, 101.5 amps for 40 minutes and do some crazy stoichiometry and come up with 10 grams. I don't know. Something, just make up something. Make their brain hurt. Make their brain hurt because they're doing that to you. Yeah, so again, all you have to do, I mean, you could, that's simple there. Well, you have to show the math. It says 1 point is earned for Huh? I agree, but you got to show where that number came from. Yeah. I don't know. Figure some way out to do this. Okay, so that is question number 3 in 2007. Now, let's look at... Okay. Let's look at another one. What copies did I make y'all next? What's the question say? Oh, I have this key. That's right. This is a little bit of Thermo. That's why I picked this one. This is question 2. Oh, man. Ow. Okay, so let's look at this question. Now, this question should, to me, it's kind of a straightforward approach. But what I want you to do is look in that AP Quick Review packet that I just gave you, and look at the part above the line, where it has case 1 through 4, and it has the sign of delta H, the sign of delta S, and the sign of delta G. Okay, so this is going to help. If you look at that, I promise you it's going to help. My first thing is let's, based on our knowledge, predict what this is. First of all, what is delta H? What is it representing? Enthalpy is, you get it, right? So when it's negative enthalpy, what type of reaction is that? Yeah, spontaneous, but what is it, exo or endo? It's exothermic. Why? It's releasing. And we know that this is spontaneous. Now, what is delta S representing? Order or disorder. This is really entropy. Now, does nature like disorder or like order? It likes disorder. Well, when this is negative, that means this is very ordered. It's very organized. Well, we don't like that. So what does that mean? It's non-spontaneous. Uh-oh, something's wrong. They're backwards. Now, look at that sheet. When it says both of them are negative, what can delta G be? Either positive or negative. Which one's which? Spontaneous at low temperatures, non-spontaneous at high temperatures. Well, there's an equation. Look in that black box right above it. What is that formula? What is the first thing they ask you to do? They ask you to solve for delta G. So the only way that delta H and delta S are related to delta G is the granddaddy of them all. Delta G equals delta H minus T delta S. And what is our temperature? Where does it say it at? Right there. Or right there. It tells us that the temperature is 298. So what do you have to do? Yes, that's a plug and chug. That is a basic plug and chug equation. So I'm hoping you can plug these numbers in. Of course, that's going to go there. That's going to go there, and that 298 is going to go right there. I do encourage you to do this on your own until you get the right answer, but I'm going to go ahead and plug it up just for time's sake. So delta G comes out to be negative 187. No, excuse me, 181. I know where the problem is. Kilojoules per mole. And I should have caught this before I ever began. And guys, this is extremely, extremely, extremely important. And I'm extremely sorry I didn't catch it. Look right here, because this always happens. People, I guarantee you, 95% of the population missed it because of those two factors right there. You cannot compare two different units. Guys, delta H is always in kilojoules. Delta S is always in joules. And I really wish I could come up with a way for you to remember that. So what do we need to do? Convert. What would be easier to convert? I would convert that to joules. So do 264,000 joules per mole. Okay. Now, why did I give my answer in kilojoules? It doesn't matter. You could also put negative 181,000 joules. Either way, it doesn't matter how you do it, but you got the same answer, right? So on this question, put check units. Extremely important, guys. You must check your units in thermo questions. Thermo, check your units. Thermo, check your units. Thermo, check your units. Now we have three factors that tell us true spontaneity. What are those three factors? No, the geek factor. The geek factor tells us true spontaneity. Well, since delta G is negative, spontaneous or non-spontaneous? Gangsters are negative. This is spontaneous. So, this must be at what temperature? Low temperature. Guys, is room temperature low temperature? Is this an average good temperature? Yes. Well, 298 is 73 degrees Fahrenheit. That's a low temperature. So, of course, it's going to be spontaneous. Are we okay? That's fine. I will leave it there as long as you need it to ask any questions you need to ask. Season 1, episode 1.
Yeah.
The second episode's actually a lot better.
Yeah.
Okay, the first one he's kind of in his underwear.
It's just like the meth in the show.
Well,
Why
okay, so now, all of a sudden, everything thus far has been delta G, delta S, delta H. And then they throw this crazy-looking letter in here that has nothing to do with thermo at all, the letter K. But I've already explained to you how you deal with the letter K and delta G. What was that equation? Negative rat link. Now, I don't necessarily like negative rat link. I like the new phrase because this is the new technology uses. Retweet the link. Whatever works. Okay. Retweet the link. It's okay. Or rat link. Whatever works for you. This? It's just RTLNK. Now, listen. What are you trying to solve for? No. Determine the temperature at which the equilibrium constant for the reaction is equal to 1. They're not asking for K. They're asking for T. So we need to rearrange this for T. And what would that be? Very good. Delta G divided by negative R ln K. Are we agreeing with that? Now, we've already determined what delta G is. All right, guys, y'all do Oh, we need to make an important point here. I tell you what, guys. Hey, go ahead and solve. No. Okay. I need to make an important point. Hang on. Guys, please listen. KEQ is equal to 1. Now listen. When K is equal to 1, where are we at? Since we are at equilibrium, can any voltage be produced? Can any energy be produced? So what does that mean? Delta G is 0. Guys, that's my fault. I should have thought about that. It caught me when I was like, wait a second. We're still on B. Huh? We're chill. Stop. I know that. No. I'm getting here for a reason. Hold on. So since we're at equilibrium. Now, when your electrochemical cell is at equilibrium, what has occurred?
The right hand side.
No, the very back of your head.
So, when we're at equilibrium, if your electrochemical cell has reached equilibrium, what has occurred? Your phone is dead. You can't use your phone. Your phone doesn't die. It does what? It reaches equilibrium. Well, when you plug it in the wall, what type of source? You've entered electrolytic. So you have reverted it back to its original form, which is galvanic, voltaic. It produces volts. So when delta G is 0, what is E also going to equal? E is also going to be equal to 0. Now, I know you're asking, we're solving for temperature. Why are you telling me about delta G and E? There's an equation we can use, and it has to do with these two things. And it's the exact same equation we used earlier. Delta G is equal to delta H minus T delta S.
Okay, what I'm thinking is why couldn't you use the 3 feet length thing?
Okay? Because when you do that, delta G would have equaled 0 and would have been 0 on top. You can't divide anything into 0.
Delta G is
So if you would have plugged a 0 in up top, everything would have been null and void. It would have been 0.
You put 0 at the bottom.
Thanks.
Delta G is 181. Blah, blah, blah.
Okay, let's try. You try it that way and I'll try it my way. You try it your way and I'll try it my way.
What needle should I use?
Stop. I'm going to plug in 0. Stop. And I'm going to plug in negative 264,000 joules minus T times negative 278 joules. Okay. So now this side's 0, so I can just subtract off and divide. So I have 264,000 divided by negative. No, it's actually, let's do plus a positive. So let's change that to a positive 278. And that's going to give me my T value. All I did was algebraically rearrange there. No, they're asking you to solve for T.
But if we use that delta H over there, that means that we already have
No.
it says 298.
Yeah, but now they're asking you for when K is equal to 1. They've changed equilibrium.
I don't see T up there at all. On the top of the wall.
Exactly. So 950. Yes. No.
There's a difference. You need to.
There's a pound and a dollar.
No, like in American English, a billion a billion is a million
Numbers
billions.
are numbers.
And a trillion is
So here's the equation I tried to use the first time before I realized we were at equilibrium. Here's the problem. The natural log of 1 is what? No, it is 0. It is 0. So if you have 0 times something, what is that? 0. So negative 181 over 0, it is an error. It will not work. So the reason you cannot use this equation is because you are at equilibrium. That means you have to go back and you have to use the granddaddy equation, which tells us, since we know we're at equilibrium, we know that delta G is equal to 0. Well, if you use this equation, plug 0 in for delta G, and use delta H and delta S, you can solve for T, which was right here. That is the right answer. Okay, so 950 Kelvin. No, it's the reason they use K is to tell you to go back to this. Okay, temperature. So it's 950 Kelvin.
even if they had left off the page, you still couldn't use the right equation.
Well, no, I mean if they gave you 2.4 times 10 to the negative third, yeah. But since you're at equilibrium, because when K is equal to 1, you are at equilibrium. That's the key. All right, say that again. Yes. I plug 0 in for delta G. Where? Because they changed it. This question is not at equilibrium. This one is. Yeah. Because you're at equilibrium. As soon as they tell you this, delta G must be 0 because you're at equilibrium. In question A, you're not at equilibrium. Well, I know. Where? I was plugging it into Rattling. You can't use that equation. That's this one right here. You talking about this one? I showed you that this would not work because if you took the natural log of 1, it's 0. You can't divide.
Even though it ends up equaling undefined, you would still use 0 joules, wouldn't you, for delta G up top? Because you can't use that because it's equilibrium.
Yeah, but so you're telling me T is equal to 0. What I was telling you is if you are not at equilibrium, you can still use this. You can use this equation if you are not at equilibrium. Let's just say instead of 1, it was 6.2 times 10 to the negative third. You can plug that in because that's not 0, right? Does that make sense? This will be the temperature you would be at this equilibrium constant. But since you're at equilibrium, this whole entire equation is useless. But it's simply, I use this because you can use this equation if you're not at equilibrium. That's the only reason you cannot use this equation is because you are at equilibrium. Okay. All right. Since everybody's leaving, I'm going to shut it down. Okay. Yes. You can take it now.
Anyways, yeah.